My name is Azer Yalin. I'm a professor in mechanical engineering at Colorado State University. I'm contributing to the team that does novel diagnostics and on the propulsion side of things. So the idea is that the SPAR program is working with very new innovative molecular propellants flowing through these electric propulsion thrusters, and so the part of the project I'm involved in is looking at the Hall thrusters in particular. And so there's been a lot of diagnostics that have been developed using the conventional fuels or propellants, which are noble gases like krypton and xenon. And so one of the important advances in the SPAR program is to explore how well these high power thrusters can work on these new molecular propellants. Diagnostics play an important role because they give a detailed characterization of the true physical details on small spatial scales of how these thrusters operate, and then that type of data is very important for the modeling team. And so the idea is to use models that can simulate both given thrusters but also optimize thrusters, explore new thruster designs. And so the underpinning or the data that goes into these models comes from these laser diagnostics. And so my research group at Colorado State University is developing essentially new laser diagnostics appropriate for the molecular propellants in these SPAR relevant Hall thrusters. And to be a little bit more specific, my team is going to be measuring what are called ion velocity distribution functions, which is a bit of a mouthful, but basically how the molecular nitrogen ions are accelerated as they move down the channel of these Hall thrusters, and that is in support of the modeling that I described. My research is in the area of diagnostics and more specifically laser diagnostics. And so the laser diagnostics provide a non-intrusive tool to study the detailed properties of the plasmas of these thrusters. And so by non-intrusive, what we mean is that we can illuminate the plasma plume with a laser, we can look at light with another detector, but those steps do not change or perturb this plasma system that we're studying, whereas physical probes in many cases can perturb the system. So the laser diagnostics are advantageous in the sense that they're non-intrusive, and so our role is to develop these diagnostics, and that will make detailed measurements of the properties of the plume of the Hall thruster, and that will be used in support of the modeling and simulation efforts as part of the SPAR program. So we have some vacuum chamber facilities and test articles at Colorado State University, where I'm from, and so we're building up our tools on these smaller sources, developing the methodologies, hopefully working out the bugs, but we're doing all of this really in preparation for the Year 2 system test, which is one of the centerpieces of the 2026 Year 2 SPAR effort, which will be testing an early version at least of this high power Hall thruster with these molecular propellants at University of Michigan in Dr. Jorns' PEPL laboratory. And so our team in the summer will be bringing this laser diagnostic sensor that we are developing now at CSU and bringing that and implementing that during an approximately 2 to 3 week campaign in the summer of 2026. So definitely very excited about that, feeling some pressure to perform and deliver useful results, but that's what we're hoping to do here. The work that we're doing in my group is really going to provide a lot of the fundamental detailed data that in turn will be used to validate the numeric model and simulation capability that SPAR is developing. And a little bit more specifically, we will be doing laser measurements of the detailed properties of the plasma plume when we operate the high power Hall thruster on the molecular propellants. And so that data will be used by the modeling team to validate and anchor the model, which will then give a tool to optimize and develop these future propulsion systems, which are really at the heart of the overall SPAR activity.